Welcome in, everybody. In this video, I'm going to go over implicit differentiation. I'm going to go over what it is and why it's important. I want to go over the process of finding an implicit derivative and some warnings that come along with it, and then we'll get into some examples at the end of the video. Let's get into it. What is implicit differentiation? Well, implicit differentiation is a technique used to take a derivative if the function is not explicitly defined. And what that means is functions defined explicitly generally come in the form of y equals something, some function with whatever variable, or using function notation, f of x equals whatever in terms of x. Whereas implicitly defined functions, the function or equation is not solved for the dependent variable. I think the easiest example to understand for this might be the equation of a circle. You have x squared plus y squared equals 1, or whatever, some perfect square number. You can solve it for y, but it makes the derivative a little more involved. So instead of solving for y, we will learn how to solve or find derivatives implicitly. So how do you find an implicit derivative? Well, the first thing you're going to do is differentiate both sides, and this is a big step. So I go into more detail on this in the examples. And then from there, you want to solve for dy dx. The only warning I have for you is you will use the product rule or possibly the quotient rule anytime you have a term with an x and a y in it. And in this video, I go over the examples almost exclusively with x and y because we graph on an xy coordinate plane, but just know that this can extend out to all sorts of other variables that you may be aware of, like a or t or theta. This is on the table for those variables as well. Speaking of circles, the first equation we've got here is a circle. We want to find dy dx, aka the derivative of this equation, but you may have noticed it's not solved for y, so we're going to use implicit differentiation. And it's really not as bad as it sounds. What we're going to do is we're going to treat the y variable as if it were an x. So when I say differentiate both sides, we're going to do this, right? So d dx of x squared plus y squared equals d dx of 9. Not bad so far. So we're going to take the derivative of x squared, and since these variables match, we just get to take the derivative as normal, so 2x. But when we move here, we're going to take the derivative of y with respect to a different variable. That means we're going to use the chain rule here. So the outer function is squared, the inner function is y. So we're going to take the derivative of the outer function, leave the inner function alone, and then multiply that by the derivative of the inner function. Now we don't know what that derivative is, right? We don't know what the derivative of y is. It's not in terms of y, but we can represent it by the derivative of y with respect to x. All right, these two terms are being added together, and of course the right side, the derivative of 9 is 0. So now you can see here dy dx, right? We've taken the derivative of both sides, and we had to use the chain rule because this variable didn't match this one. That looks like this. And now all we have to do is solve for dy dx. So of course the first thing you want to do is get all of the terms with dy dx on one side and all of the terms without dy dx on the other. So subtracting 2x from both sides will give us this. Negative 2x, there we go. And then since we're solving for this variable, we just divide both sides by 2y. So dy dx equals negative 2x over 2y. And of course we can do some simple simplifying here. Negative x over y. And that is the implicit derivative of this circle. Now you might notice too that the implicit derivative not only has x's in it, but also y's. That is important to keep in mind as we move forward. In this slide, I just wanted to take a couple minutes to explain why we use implicit differentiation. So for example, this is a slightly different example than the last slide, but maybe you said to yourself in the last example, I can solve that for y. Congrats, we got there. Subtracting x squared, taking the square root, that's fine. But now when you try to find the derivative with respect to x, you don't just find the derivative of one function, you have to find the derivative of each piece of this function. You have a positive version of this and a negative version of this. This is now a piecewise function. And you're saying to yourself, well, I can do that too, because when you separate these, it's really just the same function that you're finding the derivative of with opposite signs. So let's do that. And since you know the chain rule, you're successful in finding these derivatives. That's fine. And these look very scary, I might add, compared to what we found on the last example, negative x over y. So where it really rears its ugly head is when I ask you, what is the slope of the tangent line at the point negative 3, 4? We can't just use both of these. We have to use one or the other. And you have to know which one first. Negative 3, 4, is that in the upper arc of the circle or the lower arc of the circle? And then you have to substitute the value in. But yeah, so just because you can solve for y doesn't mean you should. Trust me. Most of the rest of the examples, you won't even be able to solve for y anyway. So it's a good idea just to get comfortable with how implicit differentiation works. That being said, let's find the derivative of this function. Once we find it, we will then find the slope of the graph at 2, 3. Okay, so let's examine this. I think the right side of this equation is going to be relatively easy to find the derivative of. But the left side, we have an x and a y in the same term. So we're either going to have to use the product rule or the quotient rule. And I promise it's the product rule this time because x is being multiplied to y. So I'm going to work on the right side of this equation first, because that's what I think is going to be easier. So 22, if we take the derivative of y normally, it just becomes 1. And then we have to multiply it by the derivative of y with respect to x by the chain rule, right? So from there, the derivative of 3x is just 3. So that part, not too bad. What I'm going to do over here is I'm going to notice that I have x cubed times y squared. And this is a product rule, as I mentioned already, so I'm going to take the first times the derivative of the second. So again, noting that y is the inside function, the square is the outside function, so it would be 2y times dy dx. Then we will add to that the second, which is y squared, times the derivative of the first, which is 3x squared. So I'm going to clean this up and explain really quickly. I remember not doing this. When you're taking the derivative of 22y, we're just taking the derivative of the y. The 22 is constant. but it's like this again. It's just using this idea that y is the inner function and the power 1 is the outer function. So the power rule, right, we would bring down the 1, subtract 1, so we would end up with y to the 0, which is just 1. So there are no more y's in this term after we take the derivative. But we still have to go through and multiply by the derivative of that inside function dy dx. All right, so on with the solving process. So we took the derivative, I cleaned it up so that the x's are first, the y's are second, the dy dx's are last. This is where we need to get all of the terms with dy dx on one side of the equation and all of the terms without dy dx on the other side of the equation. So we can do that by subtracting 22 dy dx from both sides and subtracting 3x squared y squared from both sides. From there, since we have more than one term with a dy dx, we can factor that out like this. And then to solve for dy dx, all we have to do is divide both sides by this quantity right here. And I'm going to have to continue to another slide to finish this up, because while we were successful in finding the derivative here, we still have not found what has been asked of us: find the slope of the graph at this point. So make sure you get this written down and meet me on the next slide. So from here, we're just trying to find the slope at the point 2, 3. And really all that involves is us taking these numbers and appropriately substituting them into this derivative. The derivative does, after all, tell you what the slope is if you substitute some numbers into it. So let's substitute those numbers in. There we go. Then all we have to do is simplify this monstrosity. Be sure to use a calculator for that. This is not something you're going to want to do in your head. And when you simplify the numerator, you should get negative 105. And when you simplify the denominator, you should get 26. So this is the slope of the graph at 2, 3. All right, next example. We've got some trigonometry in this one. Let's go. So we're just trying to find the derivative. This is not solved for y, so I'm going to just not try to solve this one for y at all and use implicit differentiation. So I will start on the left side. The derivative of cosecant of x is in fact negative cosecant x cotangent x. The derivative on the right side, this is technically one term on the right side, so we have an x and a y in the same term. So we will have to use either a product or a quotient rule. You can already tell it's a product rule. So first, times the derivative of the second. So how do we find the derivative of the second? Well, the derivative of 1 is 0, and this is a chain rule. So the derivative of the outside function of tangent is secant squared y. We leave the inside function alone, that's y. But then we have to multiply by the derivative of the inside function plus the second 1 plus tangent y times the derivative of the first. Well, luckily it's just x, so we're going to multiply all of this by 1. No big deal. So now we need to get all of the terms with dx dy on one side of the equation. That's this one here. That's it. No other term has dy dx. And we get all other terms on the other side of the equation. From here, all we will do is solve for dy dx by dividing by this quantity right here. And there we have it. This is the derivative of what we started with way back here. All right, in this example, we are definitely being asked to find something weird here. This is the second derivative. I just want to take a moment and explain why that is. It's like if you find the derivative with respect to x of y, and then you found the derivative of that, you can see why the square is after the d in the numerator, but after the dx in the denominator. I just wanted to point that out. So it turns out anytime you have the function x squared plus y squared equals some number, the derivative implicitly is dy dx equals negative x over y. Every single time. Go try it with that weird explanation I gave about why you don't solve for y. I promise you'll end up with negative x over y. But from here, we have to find the derivative again. And so in this case, we have one term, there's an x and a y in the same term, so we're either going to have to use the product or the quotient rule. And again, I think y'all can see this one's going to involve the quotient rule this time. So let's find the second derivative of this. That will be the denominator times the derivative of the numerator, not bad, minus the numerator times the derivative of the denominator. And I already gave an explanation of why this works. The outside function is raised to the first power, the inside function is y. So really here we're just left with dy dx all over y squared. Now the fun part about this is the following. We can't just leave the second derivative in terms of the first derivative. But it turns out we know what the first derivative is. It is right here, negative x over y. So we're going to make this substitution and then do some really clever, in my opinion, simplifying. The first time I learned about this, I just thought the simplification was so cool. So I'm getting this value substituted in here. This is y squared. And generally speaking, when you have a fraction within a fraction, you want to get rid of that as quickly as possible. So the way to do that is to multiply this big fraction here by y and y in the numerator and denominator. Now when that happens, you'll distribute the y to each of these, which is how we get rid of that there. So moving forward, it looks like we will end up with negative y squared minus x squared all over y cubed. But we can do even better than this. You might notice that this is really close to this up here. So if we factor out a negative, we can then rearrange these so that x squared is first, and we can make yet another substitution. That substitution being x squared plus y squared is 36. So we can make this even simpler just by replacing x squared plus y squared with the 36. And that is the second derivative for this function up here. Here's the final example for the video, and yes, I'm asking to find a second derivative again. And no, I've not worked this one out yet. I don't know if there's any clever substitutions or simplifying that we can do at the end, but I'm willing to take this journey with you. Right off the bat, the first term has an x and a y in it, so we're going to have to use a product rule. So 7's just going to come along for the ride. The first times the derivative of the second plus the second times the derivative of the first, minus we're here now. That's minus 4 sine of x will be minus 4 cosine of x when we take the derivative of that equals 0. From here, we can just distribute the 7. We can then move all the terms without dy dx to the other side of the equation, and then divide by anything that is not dy dx. So we'll divide by 7x. First derivative complete. All right, first derivative here, we need to find the second derivative, so let's just get right into it. This will be d squared y over dx squared equals the denominator times the derivative of the numerator, which is negative 4 sine of x minus 7 dy dx minus the numerator for cosine of x minus 7y times the derivative of the denominator all over the denominator squared. From here, I'm just going to clean this up a little bit and also substitute this in for the derivative. Again, we cannot express the second derivative in terms of the first. We need x's and y's, so this will also get substituted here. There's the cleanup. I distributed 7x here and here. I substituted this in for dy dx, and I distributed a negative 7 here and here. From here, last example, we had to multiply the top and bottom of this big fraction by 7x, but it looks like we don't have to do that here because 7 will reduce with 49 to give me 7, and this x will reduce with this x, so we don't have to multiply this fraction by anything. The only other thing that I see can happen here is we can factor a 7 out of all of this stuff and combine a couple terms. Let me factor the 7 first. So there is the factored 7, and why we did that is so we can reduce a 7 here with a 7 here, leaving us with just a 7x squared without parentheses in the denominator. Then the only other thing that I see can happen is we can simplify some of these terms in the numerator. Right, we have a minus 4 cosine of x minus 4 cosine of x. We have a plus 7y plus 7y. So just combine those, and we get our final answer for the second derivative. I hope this video helped you out.